This conference will now be recorded.
Very good morning, students. We were discussing about alternating current. As you know, we have already discussed about pure resistive circuit, pure capacitive circuit, pure and inductive circuit, and combination of LR circuit, CR circuit, and series LCR circuit also we had discussed. So what we had discussed in this, we had applied alternating voltage in series LR or series CR or series LCR circuit, and then we have seen the phase relationship between the voltage, applied voltage, and current. Okay, and each cases we had found out what are the effective resistance in the alternating circuit or AC circuit, that is called Z, that is defined like denoted by Z, that is actually called impedance. We have found out impedance, and most of the solutions we have done, analysis we have done in terms of phasor diagram method, right? And see, for LCR cases we have both used analytical treatment, so by solving equation, differential equation, and also by phasor diagram method we have already discussed. So today I'll take one part of series LCR circuit. That is actually very important, both uh, science wise or scientific knowledge wise, and also this particular thing, resonance, is used in many field of sciences. Okay, in science you may see it in technology also, while making devices, this resonance play a very important role. Okay, this resonance plays a very important role. And also when you go for atomic spectra, etc., atomic spectra or spectroscopy related anything you go for, we'll see in electronics, in many field of science you will see this term resonance. Okay, and even in case of sound, in mechanics we have seen that term resonance. So today we'll discuss what is the condition for resonance in series LCR circuit, and what is called sharpness of resonance, and how to define that quantitatively, what is called quality factor, and we'll see power in AC circuits, and what is called Wattles current. So these are the few terms we will discuss today, and these are actually going to be very interesting discussions. And these are very important terms for any competitive exam and as well as board exam. So let us go through these things. Okay, so what is called resonance? You might be aware of resonance. Okay, so I'll just recap resonance. See, this term comes actually in case of oscillations, right? Oscillations, this is very important and relevant concept for oscillations. So when I talk about series LCR circuit and resonance in that, then we have to think that there is something something related to oscillation that happens in LCR circuit as well. Okay, so resonance terms in actually oscillation. Okay, and see, there should be some natural frequency of vibration, natural frequency of vibration. You might have learned in case of post vibration. Okay, post vibration. So natural frequency of vibration, and another one is called driving frequency or drive-in frequency. Driving frequency, okay, sorry, driving or external frequency, we can say external applied frequency, driving or applied frequency. Obviously, frequency you cannot apply just like that. You have to uh, apply through wave or some kind of oscillation, right? So this driving frequency also you have to apply by some kind of force or some kind of voltage in this case, okay, some external voltage or some kind of oscillations externally, okay. So these are few terms, okay. So natural frequency is what? See, suppose you have a swing, okay, so you have swing. So this swing actually has its natural frequency of oscillation, right? A natural frequency of oscillation, and when you just push it, someone is pushing the boy who is sitting on the swing, pushing from back, okay, pushing from back. If suppose that pushing is done in a periodic manner, if that pushing is done, pushing is done in periodic manner, periodic means it has a definite frequency. So periodic manner, and frequency of that push, frequency of push, the frequency of push, if suppose that is omega somehow, and that omega is exactly becoming equal to the frequency, natural frequency of oscillation of the swing, then it is actually the amplitude of vibration or oscillation becomes very large, okay. And when it becomes very large at the condition when the driving, let us say this is driving frequency, when the driving frequency or external pushing frequency is becoming equal to the natural frequency of oscillation, that time the vibration like amplitude of the vibration becomes maximum, okay. So this condition is called resonance, or this is called resonance. So we'll see, this is actually I had just recapped what happens in case of oscillations in the mechanics. So here also the same things. See, LCR circuit has its own natural frequency of oscillation, that means it has a tendency of oscillation, okay. So LCR circuit also has a tendency of oscillation. Now when we apply external AC voltage, there is a frequency, right, in the AC voltage. So in the applied AC voltage, suppose what we do, we have a signal generator which can supply continuously some alternating frequency or sinusoidal frequency, sorry, sinusoidal wave or signal. So suppose I have LCR circuit where I have used where this one is a signal generator which can send sinusoidal voltage, okay, voltage which is actually varying sinusoidally, so it has some certain frequency, but this frequency, so with signal generator I can actually vary the frequency as well, okay. You might be seeing in your basic courses signal generator where we can actually vary the frequency. This is angular frequency, we can write this angular frequency as 2 pi f is equal to omega. So let me say this f is the frequency, normal frequency, which has a unit hertz. So this frequency can be varied. Okay, this frequency can be varied. Okay, so suppose 50 hertz to 500 hertz. So I can use different kinds of combinations of this L, C, and R and vary the frequencies, like see this source voltage. See this voltage through signal generator. I can vary with various frequency. Like I just fix one amplitude, particular amplitude, and I can actually vary the frequency in the circuit. Okay. So at some certain point we'll see here this R, I can use many R I can use, and you look here what is happening. See, as we vary the frequency, we can actually you know what we can do, we can vary the frequency as you said. See one thing here, I0, what is I0 in LCR circuit? I0 is actually V0, where V0 is the amplitude of this, okay, this applied sinusoidal voltage omega t. Okay, so V0 by Z. What is this Z? This Z is square root of R square plus 1 over omega c minus omega L whole square. Okay, so this is actually called impedance. Okay, this is Z, this is impedance, and you see here the value of the current depends on, see, the frequency, right? Value of the current depends on frequency as well as R. If I use different R, just keeping the same L and C here, see the maximum amplitude of the current that varies. See, when I use more and more resistance, then you know I get lesser and lesser amplitude of the current because of this, because this amplitude of this impedance increases, right? So that part is one part, you can see that. So the see the phase doesn't depend on phase does not depend, so phase does not depend on the resistance of the circuit, because in pure resistive circuit we have seen that the current and the voltage are in the same phase. Okay, but the amplitude of the current as well as the resonance depend on the resistor. Okay, because this see for different resistance we get different amplitude of the current. Now see what I do, I just use the signal generator and vary the frequency from some omega to some, like omega 1, omega 2, omega 3, like that different frequencies I apply and see what is the current. And at certain point of time we'll see, let us say that frequency is omega r. That particular frequency, at that particular frequency we'll see the amplitude of the current is maximum, like it is showing the peak. And as we deviate from that resonant frequency or that particular frequency, the current is decreasing on either side. So what I say, if we vary the applied, like vary the frequency of the applied voltage, alternating voltage, we see at certain frequency, at particular frequency, the current source a peak, and on either side of that frequency the current decreases. Okay, so this particular frequency is called resonant frequency. Okay, that particular frequency is called resonant frequency. That means at the LCR circuit has a natural tendency of oscillation, and it has certain natural frequency. Let us say that is omega 0. Okay, and so the external applied frequency, which is omega r, according to our observation, when that is actually becoming nearly equal or exactly equal, that time the vibration, amplitude of the vibration, or in this case we'll say the amplitude of the current becomes maximum. Okay, amplitude of the current becomes maximum, and this maximum value of the current depends on the value of the resistance. Now let us see what is the condition for this resonance. When the current will be maximum, what is the, see here I0, when I0 will be maximum, this will happen when I0 will be I0 max when Z is minimum, when Z is minimum, right? So when will be Z minimum? Z will be minimum when, so this Z will be minimum when this term, we can see this particular term becoming 0. I'll just write it down in the next page, or let me just erase. Okay, so Z will be minimum when omega c, 1 over omega c minus 1, minus omega L, omega into L, this term in the impedance becomes 0. Then Z will be simply R. Okay, Z will be simply R. So this is the minimum impedance actually. Okay, minimum impedance, and then the current will be maximum. Okay, so current will be, then what will be the current then? I0 max. This will be simply V0 by R. Okay, V0 by R. So we are now concerned with the condition. What is the condition for resonance to occur? Okay, so condition for resonance, so what is the condition for resonance? That is omega L becoming equal to 1 over omega C. Okay, or from here we'll find out the particular frequency. Let us say that is omega 0. Okay, let us say that particular frequency when this omega L, I'll explain what is this omega L also. So omega, let us say that these are omega 0, that particular frequency is omega 0 when this, okay, we have taken omega R. Let us just keep uniformity. So this is omega R. So omega R is equal to 1 over root over LC. Okay, so this is the condition. And see, if we want to go with linear frequency, FR will be 1 over root over, say 1 over 2 pi root over LC. Okay, so this is the condition for resonance. I'll just erase this part. What is the condition for resonance? When the frequency, external frequency becomes 1 over root over 2 pi 1 over 2 pi root over LC. Okay, so this is, we can actually write this in this way also, root over 1 over LC. Sorry. Okay, so this is called resonant frequency. So there will be frequently numerical problems from this particular condition for resonant frequency. You will be given L and C. So you can see that resonance does not depend on resonant frequency, does not depend on resonant condition of resonant. Actually resonance can happen in any resistance value. So resonant frequency does not depend on resistance. That means resonance can happen in any resistance. Only the sharpness or the maximum value that depends on resistance. It depends only on the value of LC. So what is this actually? Omega L and 1 over omega C. I'll explain here. Sorry. Okay, let us go to this place. Okay. So what is omega L and what is omega 1 over omega C? See, if you remember, this is actually XL, okay, which is the inductive reactance, and what is 1 over omega C? That is actually XC. This is capacitive reactance. Okay, capacitive reactance. Now see, if we actually multiply IRMS with XL, then we get VL. That is the voltage drop across the inductor. And if I multiply IRMS with XC, then we'll get VC. That is the voltage drop across capacitor. So look here, what is the condition for actual condition for resonance? When the voltage drop across the inductor coil becomes equal to the voltage drop across the capacitor, then they will cancel each other. If you remember the phasor diagram, suppose this is current and voltage, both are in the same. So VR is along this direction, isn't it? So VR is along this direction, and see, this was VC. So current and voltage drop across the resistor will be in the same direction, no phase difference between them. So this is VC, and this was exactly in the opposite direction. They have actually 180-degree phase difference, like this. So this is VL. If these two are the magnitude of these two are the same, then actually they cancel each other. So all that drop, see, the whole voltage at this condition, the whole power, whole potential, okay, so potential, let us say the whole potential drop across the resistor. Okay, so whole voltage actually drops across the resistor. Okay, so this is another way of saying the condition for resonance. Okay, Okay, so this is the condition for resonance. So if there is no, like, if suppose, see, I have LR circuit, series LR circuit. So why don't we see resonance in LR circuit? Because see, VL and VR, they have 90-degree angle. Okay, there is no 90-degree phase difference, so there is no way to cancel each other. Again, if we just replace this with just capacitor, then also we don't see any resonance, because see, VC, that is the voltage drop across the capacitor, and VR, voltage drop across the resistor, is having pi by 2 phase difference. Okay, so here also there is no cancellation of the voltages. All right, so you know, you should have both the components like L and C to have oscillations as well as, so we'll see LC oscillations later. So only when both L and C will be there in the circuit, there will be a resonance occurring. Okay, otherwise it is not possible. All right, so you can see few points. We will discuss some characteristics of resonance. So we have already seen what is called resonance. Okay, maybe I'll just clean some things. So see, condition for resonance, we have learned already. What is that condition for resonance in LCR circuit? Okay, condition for resonance is actually XL is equal to XC. That implies omega L is equal to 1 over omega C. Okay, so from here we get resonant frequency that is suppose FR, and this is 1 over 2 pi root over LC. This is actually resonant frequency. And see, we have seen, so one good point to write. So condition for resonance, so condition for resonance does not depend on, or resonance does not depend on, or resonance occurs in any frequency, at any frequency, I'm sorry, so at any frequency, at any applied frequency. Okay, so these are the things we have learned. Now we'll just discuss some characteristics of resonant circuit. Okay, so impedance is minimum, or the circuit first is actually the circuit becomes purely resistive. So all the voltage, okay, becomes, I will not write circuit is, okay, resonance circuit is actually purely resistive circuit as VL cancels VC, as VL cancels VC. Okay. Second point, the power dissipation in the circuit becomes maximum actually. Okay. Power dissipation in the circuit becomes maximum. Okay. So that is actually, and that is equal to V0 square by R. Okay, so this is actually this V0, I think I should write in terms of RMS. So V RMS square by R. So this is actually the maximum power dissipation happens in resonance circuit. So in this case, in case of resonance, since it is purely resistive circuit, current and voltage becomes like phase difference becomes zero, since purely resistive circuit. Okay, and so this power factor, there is something called power factor. I think we have discussed already, or maybe we'll be discussing power factor, which is actually cos phi, that becomes equal to 1. That becomes equal to 1. Okay, few more points are there. Okay, so I'll discuss those also. So this happens actually for all values of resistance that I have already told, and also I have told that in this case VL cancels VC, that I have already told. And for larger value of R, maximum current, amplitude of the current decreases, and for smaller value of resistance, the maximum value of the current in the circuit will be more. Okay, that means current will be larger as the resistance decreases. Okay, so so these are few points. Okay, so one more good point I'll tell you here. See, if you apply, see actually this at the resonance condition, resonance frequency alone, so the series resonance circuit is also called acceptor circuit, because when you feed a number of frequencies to the circuit, it accepts the power or accept the frequency only at the resonance condition, or the resonant frequency alone it will accept. So the resonance circuit accept power from the source at the resonance frequency. Okay, so if you have applied various signals, okay, so only the signal with the frequency of resonant frequency will be accepted by the circuit. Okay, or it takes the power at that particular condition. Okay, at that particular frequency. All right, so these are few points. I think I should write the last point. So resonant circuit is actually resonant circuit. Resonant circuit is an acceptor circuit. Acceptor circuit. Okay, acceptor circuit. Okay, so I have already discussed. You can just elaborate it, that at this particular frequency, power is absorbed or accepted or signal with the frequency of resonant frequency will be accepted by the circuit. Okay, all right, we'll just go to the term sharpness of resonance. So we have seen that resonance occurs at all resistance. That means resonance does not depend on the condition for resonance does not depend on resistance, but the curve or the value of the current you can here in this figure, it is given in terms of RMS current, doesn't matter, but you can see here the resonant frequency is denoted by omega 0, which is actually 10 to the power 7 rads. Okay, uh, radian per second, okay, rad per second. So this is the resonant frequency for this particular circuit given here, and you know these are the components given. See, capacitance is used how much? 2 nanofarad, and the inductance or inductor of inductance 5 micro Henry has been used, and at that particular see with this circuit elements, R is varied actually. R is varied 10 ohm, uh, 10 ohm, then 5 ohm, and then 3.5 ohm. Okay, or maybe from 3.5 ohm to 5 ohm and 10 ohm, like that. It is varied from lower value to higher values. And see the applied voltage is given as suppose 5 millivolt. So in that particular case, the frequency, resonant frequency depends on this particular component, that is L and C. So depending on that, the resonant frequency is 10 to the power 7 radian per second, right? And here you can see that the maximum value of the current, not only the value of the current, the shape of the resonant curve. Resonance curve always will have a peak at the resonant frequency. I'll just in general tell you. So resonant curve will be always of bell shape. In the temple there is a bell, or in the church there is a bell. So it has a bell shape. This is kind of a bell shape curve. This is resonant curve, typical resonant curve. What is that? At the resonant frequency there will be maximum or peak, and on either side of this resonant frequency, this current will be decreasing. This is the nature of the resonant curve. Okay, so resonant curve will have this kind of characteristics, but uh, this can be narrower, or maybe it can be wider. Okay, that doesn't uh, that just depends on the resistance value. Okay, so this could be like this also. So you can see as the resistance is increased, the maximum value of the current decreases, as well as it become wider and wider. See, at 10 ohm resistance it is becoming so wide, but the peak occurs at the resonant frequency. So resonance is happening, that is no doubt, because there is a peak. So resonance is occurring at the same frequency, whereas the curve is becoming wider and wider as you increase the resistance. So this is actually, see, as you decrease the resistance, the curve becomes sharper and sharper. So this particular nature is, or this particular thing is called sharpness of resonance. Okay, that means, okay, so we'll just define what is called sharpness of resonance. Uh, Actually, sharpness of resonance can be defined in terms of a factor called quality factor. So sharpness of resonance can be defined in terms of a quality factor. We'll come to that, but visually you can see that. So visually you can see as the resistance decreases, or for the lower resistance, the curve is becoming so sharp and narrower, but for the higher value of resistance it becomes wider. But one thing is very surprising, that at each resistance this uh, frequency of resonance is actually becoming not changing. It is the same, because the resonant frequency does not depend on R. It depends on only L and C component. Okay, that is the reason that the resonance is happening or peak is occurring at the same place, but it is becoming either wider or narrower depending on the value of resistance. So sharpness of resonance actually depends on the resistor, okay, resistance. Okay, so to understand sharpness of resonance, we have to define a factor called quality factor. Before we learn quality factor, we need to actually learn what is called bandwidth. Okay, what is called bandwidth? All right, so what is called bandwidth? We'll see. See, I have resonance curve, typical resonance curve you can see here. Bandwidth is actually the difference between two frequencies. So bandwidth is actually defined as two frequencies, omega 2 minus omega 1. I'll tell you what is this and from where I have got this. So omega 2 and omega 1, but what are those values? Actually, these frequencies are those frequencies where on either side the current become 1 over root 2 of the maximum value of the current. So these are the frequencies where the current become 1 over root 2 times the maximum, or I can say V0 by I0 means R, right? So V0 by 2R. This is max or amplitude. Okay, so this is how this is V0 max means this is nonsense to write max. This V0 is fine. So this is also, I will not write V0 max. Okay, let it be. Okay, V0 max. Okay, so V0 max by root 2. So when V0 by root 2 into R, or I0 when the maximum, see the peak has some maximum value. So when the current becomes 1 over root 2 times the value of the peak. Okay, so suppose these are two frequencies where the current becomes 1 by root 2 times the maximum. Okay, and let us say, see this is, see in terms of resonance, if we see this omega 1 is, see this difference is same actually on either side. Okay, this difference is same, this is also delta, this is also delta. Let us say, not let us say, it is actually, it is. So omega 1 is, see omega resonance frequency minus some delta value. Okay, and this omega 2 value is omega r plus some delta value. Okay, now if you take the omega 2 minus omega 1, so this is the difference. So this difference is actually 2 delta. You look, see 2 delta. I say okay, this is delta omega, not delta, this is delta omega. I'm sorry, this is delta omega. Delta omega. So this difference will be actually 2 delta omega, which is actually bandwidth. Okay, so what is the formal definition? I think I have to erase this part. Here I have given you the definition, formal definition of bandwidth. It is the difference between two frequencies taken on either sides of the resonant frequency in such a way that the current amplitude becomes, okay, so this is 1 by root 2 times the maximum value of the resonant value at resonant frequency. Okay, at resonant frequency this is the maximum I0 max, and 1 by root 2 times this value I0 max is becoming at omega 2 and omega 1. See omega 1 is omega r minus delta omega, and omega 2, see omega 1 is omega r minus delta omega, and omega 2 is actually omega r plus delta omega. Okay, now you take the difference, you get 2 delta omega, which is actually called bandwidth. Okay, so bandwidth is actually 2 delta omega. Okay, now we will just proceed to the term quality factor, which is actually quantitatively define the sharpness of resonance. What is quality factor of a series circuit? Series LCR circuit. So it is defined as, quality factor is defined as the ratio of of resonant frequency to the bandwidth to the bandwidth okay, bandwidth. All right, so it is mathematically defined as Q is equal to, see, resonant frequency, say omega r, bandwidth is omega 2 minus omega 1 or omega r by 2 delta omega. Okay, this is actually quality factor. Quality factor is denoted by Q. Okay, now actually we can do a lot of numerical, like we can have this relation in terms of L, R and C, etc. Okay, this components in terms of this component. Okay, we can have this in terms of this component. For that, you know what we have to do, we have to find out this delta omega. What is actually delta omega? Let us do one thing. See, we have seen in case of Z, see, at resonant frequency what happens, you know, uh, Z becomes what? Z becomes 2R, root 2 into R. You might be thinking, what is this? I'm sorry. No, this will be actually at resonance condition, it is R. That is fine. But this Z becomes root over this at omega 1 and omega 2. I'll show you here how it is. See, omega 1 is this part, right? This part is what is the current? So current is actually I0. See, here I have written. So this is actually effective Z prime, right? This Z prime here is what? Z prime is root over 2R, right? So at omega 1 current is, or omega 2 current is becoming I0 max by root 2, which is V0 by root 2 into R, because V0 by R is I0, so V0 by root 2R, and then see, this is actually the effective impedance, so impedance become root 2R. So that is what I was trying to say. So this is this one. Okay, now see, I'll put it here at the expression for the impedance. We know this is omega square plus omega L minus, or vice versa, actually 1 over omega C also we could write front, because the square doesn't matter if I write this term first or this term first. Okay, so this is actually becoming root over 2 into R. Now if we square both side out, so what we get, omega square, and this becomes omega L 1 over omega C whole square. This is 2R square. So this gives me, you know, this gives me, suppose for omega 1, so this gives me omega 1L divided minus omega 1C is equal to plus or minus R. Okay, this I can write, you can just see that. So this, okay, let me just first write this itself, just omega plus or minus, it becomes plus or minus this R. I can take plus for omega 1. Okay, I think I can take minus for omega 1 because it is C, so the current is this side, So I can take this anyway. I can just take anything. So I can take, see, we get omega L minus omega C is equal to plus or minus this. So I can write, say, this minus R, and this 1 over omega to C. Okay, sorry, this omega 2 and into L, omega 2L minus of 1 over omega 2 C to be plus R. Okay, these are two equations. If I add them up, first let us add them. So what we get? If we add them, omega 1 plus omega 2 into L minus, this will be 1 over C, 1 over, minus I have taken common, so 1 over omega 1 plus 1 over omega 2 is equal to 0 over here. I'm just adding 1 and 2. Okay, so this term I'll just do the LCM and write directly omega 1 plus omega 2, omega 1 plus omega 2 divided by omega 1 omega 2, right? So this is the thing we have got. On the right hand side there is actually 0 term. So what we'll be getting, from here, see, this term will cancel each other if I just write in terms of equation, since 0 was there. Okay, that I could do. So then, this will get you omega 1 omega 2 is equal to what? It will be 1 over L and C. If you are confused, let me just give the steps here. Omega 1 plus omega 2 is equal to L, and we can write, because in, so okay, there was this omega 1 plus omega 2 over omega 1 omega 2, this is equal to 0. So I have just made it to equation like this. Okay, and then I have just found out what is omega 1 and omega 2. Okay, so this calculation I am just erasing and writing the value itself, because okay, this will be 1 over LC. Okay, now see, we had equation omega 1 L 1 over omega 1 C is equal to minus R, and we had omega 2 L plus R. So these two equations, if I just subtract, okay, see, I'll do in the right hand, subtract 2 from, sorry, subtract 1 from 2. So what we'll get? Omega 2 minus omega 1 into L. Okay, and see, subtract means 2 are will be here, and this term will be actually subtracting. Okay, let me just do this. Omega 2 minus omega 1. So 2 1 we are just, let me take 1 over C common. So I'm taking, subtracting this from this. So there will be is equal to 2R or minus 2R from 2. Okay, this will be plus only. Okay, so here you can see omega 2 minus omega 1 into L. This term is okay. This is 1 over C. This will be omega 1. So this will be plus, then omega 2 minus omega 1. Let us make this, and this is omega 1 omega 2 is equal to 2R, right? And you know this term we know already. Okay, so we can just take this common to omega 2 minus omega 1. This is L plus, see this is actually I have taken common, right? So omega 1, this was actually say 1 over LC. So I'll just take common. See, in place of this, we'll write L into C. No, 1 over L. So we'll write LC here, and 1 C was here. Okay, 1 C was here. If you see that, I'm just putting the value of omega 1, omega 2. That's all. Okay, this goes up. So 2 are here, and here we got omega 2 minus omega 1 into 2L is equal to 2R. Look, this 2 goes off, and then we get what is called bandwidth omega 2 minus omega 1 is equal to R by L, right? This is the thing we need to find out. So what we get, I'll just erase this part. Okay, it is this part. Omega 2 minus omega 1 is equal to R by L, right? This I have got. So what was the definition of quality factor? There was omega R divided by omega 2 minus omega 1, so which we have already got. See, for this I can write 1 over LC, root over of LC I can write. Okay, let me first write this omega R, and this is R by L, that means L by R. See, in terms of resonant frequency 1 over root over LC, then what I can write is L by R into root over LC, and this root will be giving you 1 over R root over L by C. Okay, so this is ultimate this thing, one expression. So this is in terms of L and R. See, L and C and R, L, C and R. This is quality factor, definition of quality factor. Okay, we had already found out here definition. So this is the definition, but we wanted to write in terms of R, L and C. This we have got now. Okay, and say in terms of C and R also we'll get that, you know, that we'll get. Let me just go here. I'm sorry, here itself. Say we want to find out quality factor in terms of, see, this is omega R divided by omega 2 minus omega 1, where we have got this omega 2 minus omega 1 is R by L, so L will go there. Now see, this is the omega R into L, so this is actually at the resonance condition, this is impedance. If I just multiply IRMS, this divided by IRMS into R, these are actually the ratio of voltage drop across the inductor to the voltage drop across the resistor, isn't it? Or the applied voltage itself. Okay, this is actually equal to applied voltage, because at resonance condition V into VR. Okay, VR at resonance condition, VR is actually equal to the applied voltage. Okay, I'll write in terms of language. Okay, let me write it here. So this is actually voltage drop across across L or C, also the same thing it will be, and applied voltage. Okay, quality factor is defined in that term also. See, this quality factor, another definition we can do actually. See, we can just multiply. So we have got this by this, right? We can multiply omega R both in the numerator and denominator. We can do that. So this is actually L, and this is omega square, omega resonance frequency square means LC into R into omega R. So what we get? This. So we get omega R resonant frequency into C into R. So this term also. So there are various ways to express quality factor. Okay, quality factor can be expressed in terms of CR, that means capacitance and resistance, and this is and resonant frequency in terms of applied voltage across the. See here, I can just multiply. I can multiply. See this, I can write XC into IRMS, right, and IRMS down into R. So we can write this as VC divided by C. X means 1 over omega R into C, and this is VR. Okay, so this is another way. So this is voltage drop across L or C divided by applied voltage. Okay, I think it is already the time. We'll just stop it here for today. We could discuss only the resonance in LCR circuit and surface of resonance quality factor. Next day we'll learn about power in the AC circuit and Wattles current, etc. And also from here we'll learn one more thing here, that is choke coil. Okay, in the next class we will discuss this power in the AC circuit. Power in the AC circuit. Next class we'll see in the next class. Power in the AC circuit and choke coil and Wattles current, etc. We'll discuss. Okay. Okay. So thank you for your patience. Bye for today.